All right, folks, we're going to go through a couple of demos that are really critical for understanding the concepts behind projectile motion. So the first one, Alan is calling shoot and drop. Um, I tend to call it drop and shoot. But we will let Alan be Alan. He can do him, and I will do me. Sped this up a little bit. He's setting this up just to show you he's got a purely vertical pole. And then he's adding a purely horizontal launch contraption. And that I want you to understand how this contraption works. Um, so there's a spring, and what he's going to do, it's a compression spring. You can see the coils are kind of spread out. He's going to lock that compression spring, and this bar is going to move to the left. He's going to place a pool ball, little yellow pool ball here, and this pole here is going to support a second ball with a hole in it. So see, he's locking that in, and then the one on the left, when he hits the button and the compression spring pushes out, that's going to retract this bar, and this ball is going to drop from rest. At the same time, it's going to launch the second ball. So, classic question, and this was one of the questions on the pre-test multiple choice series. The question is, so the story is, you're in a desert and you drop a bullet and you shoot a bullet completely horizontally. That's why you had to make sure I use the level there at the same time. The question is, which ball hits the ground first? So he's going to lock and load it. And then the answer is they both land at the same time, because neither one had any vertical motion. So what we're going to do in this unit is do our physics Sudoku in the horizontal dimension and in the vertical dimension. And both of them had an initial vertical velocity of 0. Both were being pulled down by gravity at the same rate. So they land at the same time. You might say, well, this one traveled farther, but it also had some forward motion. So the forward motion was exactly what it needed to go forward and down, forward and down, forward and down. Okay, so the moral of the story of this demo is that the additional horizontal motion of the ball on the right did not affect its vertical motion. Okay, horizontal and vertical, got to keep them separate. All right, and this is a beautiful animation just to illustrate it, that if you pause this video at any point, the green ball and the blue ball are always at the same height. And you can see that if you just focus on the vertical motion, the distance between each image is increasing because it's speeding up. But if you focus on the turquoise ball's horizontal motion, it goes the same horizontal distance every time. So that's another important concept, is that projectiles, the horizontal speed, unless there's a jetpack or air resistance, but in general, a classic projectile problem, the horizontal speed is constant and the vertical speed is changing. And they both land at the same time. Okay, so the first demo was drop and shoot. The second demo I call the Batmobile. All right, sorry about that. I call this the Batmobile. I'll show you that person on the cart in a second. But so I call this the Batmobile. The Joker has stolen the Batmobile, and there's an ejection seat. And so what you're going to see is, while this cart is traveling from right to left, this marble is going to be ejected up in the air. So the question is, does the Joker, so Joker's on the Batmobile and Batman hits the ejection seat. So the question is, does the Joker land in front of the cart, back in the cart, or behind the cart? And remember, the cart is traveling from right to left. So I want you to notice, if you pause this video at any point, the Joker is always directly above the Batmobile and boom, lands back in the cart. All right, so the moral of the story of this demo is that the additional vertical motion did not affect the horizontal motion. That it's the Joker had the speed of the Batmobile when they were in the car. That's why if you throw your peanuts or snack up in an airplane, it doesn't go flying to the back or the front of the airplane. You don't notice that you're in this moving airplane as long as it's moving at a constant speed. Joker had that horizontal speed. Joker has inertia, so he's going to maintain that horizontal speed. He only gained, the only outside force on him was this, there's a spring in here. The spring pushed him up and then gravity pulled him back down, but that up and down motion is completely independent from the left and right motion. Okay, I didn't want to show this video. It's kind of cool, but I'll explain as I do it. All right, sorry, we're just gonna have to watch it like this for interest of time. All right, so Professor Leap physics demonstration. So he's throwing the ball up. So this is without, he's on a cart, without the cart moving, it's clearly going to come back and land back where, from directly below where he threw it. And then his friend's going to push him. And what I don't like about this is they don't explain, like the ball continues forward. So I think I'm guessing what happened was there was friction with, and so he slowed down, but the ball didn't. So then the friend's going to compensate for friction and maintain his constant speed, and then it will come back and he'll catch it. Okay, so this is the third classic demo, and the first one showed extra horizontal motion doesn't affect vertical, the drop and shoot. The second one, the ballistics cart or the throwing the basketball, proved that the extra vertical didn't affect the horizontal. This is a little bit different, but again, a classic demonstration. Oh, you know what? I'm going to speed this up. And thanks for your patience. All right. So, large MIT demo hall, and of course, you can't do an experiment without a white lab coat. So this stuffed monkey is placed up from a specific height. And when I tell the story in our demo, I say it's Monkey Goes to Murray Homecoming, and there's a t-shirt gun, which is launching metal spherical t-shirts. Oops. So Professor number 2 loads the gun, and boom. Oh, I forgot to ask the question. So they're going to show you in a second the laser, the t-shirt is aimed for the monkey. So if they did this experiment in an area without gravity, the monkey, oh sorry, I totally forgot to set this up. So there's an electromagnet here, and when this is launched, the electromagnet turns off, which releases the monkey. So the story is the monkey sees the gun and gets scared and drops from the tree. So there's a bunch of equipment to make sure that the monkey falls, that the instant the bullet is shot. Okay, so if this experiment were repeated on a planet with in a situation where there's no gravity, the monkey would just hover and the bullet would travel a straight line path and hit the monkey. Okay, so the moral of the story of this demo is that if two things would collide without gravity, what's pretty cool is you can run through the math. They will collide at the same time with gravity, but at a lower position. Okay, another way of saying this is both objects fall away from their gravity-free path at the same rate. So you could say bullet goes forward, falls, bullet goes forward, falls, bullet goes forward, falls even more. Monkey falls, falls even more, falls even more, right? So you could trace what they would do without gravity and correct for gravity every so often, and they're going to hit they're still going to be at the same spot. Okay, and they're going to do this in slow motion, so maybe you can see that.
Uh,
Oh shoot. Okay. And I thought they showed the laser beam. Okay, but anyway, those are the classic demos. If you want more, you can search for Mythbusters recreated the drop and shoot demo with a real gun. So you can find that online. Thank you for listening.